Today we are going to talk about physical quantities. So we start off by what is a physical quantity. A physical quantity is a measurable that consists of a magnitude and some units of measurement. Then there are two types of physical quantities, which are, number one, we have the base quantity. A base quantity is a quantity on the basis of which other quantities may be expressed. Then the second type of quantity is the derived quantity, which is a quantity that can be expressed in terms of a base quantity. So we look at SI units for base quantities. We have 7 of those, but we'll discuss 6 for now. The first one is length, which is measured in meters. The second one is time, whose SI unit is seconds. Then we have electric current, the SI unit being the amps. The mass is measured in kgs for SI units. We have temperature in kelvins, and we have amount of substance, which is measured in moles. Now we look at derived quantities. A derived quantity comes from an equation, and this equation allows us to express the derived quantity in terms of an equivalent base units. Example, we have the Newton, which is a unit for derived quantity force. So force comes from mass times acceleration, which implies the Newton is equivalent to kgs for mass multiplied by meters per second squared for acceleration. Then you take a look at Pascal, which is the unit of pressure. Pressure is connected with the formula force over area, which implies our Pascal would be equivalent to kg meters second to the negative 2 divided by area in square meters. And in the end, we end up with our Pascal being equal to kg per meter second to the negative 2. Then we take a look at derived quantities. Other derived quantities, we have volume, which is in cubic meters because we are multiplying lengths in 3 dimensions. Work done is force times distance, and this is going to give us a unit of the joules, and our equivalent now would be base units for force times meters, and this gives us kg meters to the power 2 seconds to the negative 2. Then for power, that's work done or energy transferred divided by time, and the derived unit is the watts. And for work done now, we got the base units from the previous example. We divide that by time in seconds, and we end up with kg meters to the power 2 and seconds to the power negative 3. Then the other quantities that you can take a look at are momentum. You can also do for electric charge, and you can also do for resistance. I would want you to express those in terms of their base units. Then we look at homogeneity of equations. What do you mean by the term homogeneity? An equation is homogeneous if the quantities that are on either sides of the equation can all be expressed in terms of the same base unit. For an example, we have S is equal to ut plus half at squared. S being displacement is in meters, u being initial velocity is in meters per second, multiplied by the units of time, which is seconds, plus half is a constant, it doesn't have units. Then we have acceleration, which is in meters per second squared. Then we have time squared, which is seconds squared. All of this evaluates to give us meters, which shows that this equation is homogeneous. Now we take a look at pressure, which can be calculated as density times acceleration due to gravity times depth. So we know this to be P is equal to rho GH, rho being our density, G being acceleration due to gravity. So pressure now being also force over area should be equivalent to our density mass over volume times G times H. So we put the units, base units for force over square meters. Then we also put the base units for the right hand side. And in the end, we are going to have a homogeneous equation comprising of kg per meter per second squared. So it's homogeneous. Then we take a look at magnitude of quantities. So if a quantity is very large or if a quantity is too small, we need to use a prefix so that at least the quantity becomes more presentable and it becomes more compact and easier to work with. So we have the following scale factors that we can use for large quantities. So we have 10 power 3, 10 power 6, 10 power 9, up to 10 power 12 that we can use. So 10 power 3 represents the kilo, then the mega is 10 power 6, the giga is 10 to the power 9, the tera is 10 to the power of 12. So all these you can use as prefixes for large quantities. Then for the smaller quantities, what do we have? The powers, they progress from 10 to the negative 1, negative 2, negative 3, and of course in multiples of 3 up to 12. So we have the deci, the centi, the milli, the micro, the nano, and the pico. So you use these for smaller quantities. Now let us look at estimation. We want to look at significant numbers. How do we round off our numbers in our physics? So all non-zero digits are significant. Any number that is not a zero is going to count as a significant number. Then also, when it comes to zeros that are existing between two non-zero digits, those zeros, they are significant. So like if you take a look at this example, we have 105.003. All the zeros there are significant because they exist between two non-zero digits. Then all leading zeros are not significant. Like in this example, the 4 zeros that are before 253, they are not significant. So the only significant digits that we have right there, there are 3 of them, 2, 5, and 3. Then trailing zeros are significant, whether there is a decimal comma or not. Trailing zeros, they count as significant digits. So like in this case, the 0 after the 5, the 0 after the 9, both of them are significant. Then we look at estimation of physical quantities. In this part, you are just required to estimate day-to-day quantities within reasonable parameters. So an estimate is not precise, so you can use either 1 or 2 significant figures. So we could give some examples where we have the mass of an adult male. Roughly, this could range probably between 50 to 80 kgs. Length of a football field, we can estimate that to be 100 meters. Then we take a look at scalars and vectors. Scalars and vectors. What's a scalar? It's a quantity that has magnitude only. It only shows the size. So what examples do you have? We have mass, we have temperature, we have distance. So there's no direction involved in scalar quantities. Then we take a look at vectors. That's a quantity which consists of both a magnitude and a direction. So the examples would include force, velocity, displacement. So these have direction. Now we take a look at how we add and subtract vectors. If vectors are in the same direction and vectors are in opposite directions, what happens? So we have these two vectors, 8 newtons and 3 newtons, they're in the same direction. So it means they will add up both as positive and we end up with a resultant of 11 newtons in that same direction. Then we take a look at now these two vectors going in opposite direction, we end up with a net of 5 newtons in the other direction.